Hello, linear algebra students. Let's just have a brief discussion about why a plane that does not go through the origin is not a subspace of, say, R3 or generally Rn. And I'll start with this, which we talked about at the beginning to introduce the chapter, which just talks about what are the types of subspaces we will see, subspaces of Rn. We always have the zero vector as a subspace. We always have lines through the origin. We have planes through the origin. And then we would have, say, three spaces through the origin and things like this. All of Rn is also a subspace. But really, the definition of a subspace came from three properties. And this is from the notes. This is here. These three properties. We have a subspace provided 0 is an element of the set. This one is called closed under addition. What it says is if you have two vectors in your set, then their sum is also in the set. This one is closed under scalar multiplication. It says if you have a vector in the set, say W, then any multiple of that vector is also in the set W. Okay, and these were a few examples from class about examples of subspaces and non-subspaces. But we saw in our worksheet an example of a plane that did not go through the origin, and I quickly justified it was not a subspace because this one fails. But let's look at that example a little bit more closely and geometrically right now. What we're looking at in green is exactly this plane in R3. It's the set of x, y, z such that 3x minus 5y plus z equals 1. And we can tell just looking at it. 0 is not on this plane. 0 is the blue dot here. And so this plane is not a subspace, fails the first property. But we can also see that this set is not closed under addition. It is not closed under scalar multiplication. So let's take these two vectors here. These two gray vectors are on the plane. You can see it visually, but also you can check that the points 1, 1, 3 and 1, 0, minus 2 satisfy the defining equation, 3x minus 5y plus z equals 1. Well, what happens when I add these two vectors? Let me get rid of the plane for a second. How do we add vectors in as arrows? Well, we could do, say, Parallelogram Rule, and then we would connect, which is here. So you see this purple vector is the sum of the two gray vectors. Now let me remove both of these and go back to our plane. You see this purple vector is not on the plane. So this justifies geometrically, thinking about vectors as arrows, that this plane is not closed under vector addition, but also the third property, scalar multiplication, being closed under that operation. This does not hold either. Let's just look at this vector. Lies on the plane. And if we take minus 1 times this vector, it's here. You see, this is not on the plane. So by looking at this plane and arrows and thinking geometrically, we realize that this plane fails all three properties of a subspace. I think the easiest one to justify was that 0 is not on the plane, but all three properties fail here. Definitely not a subspace of R3. So thank you very much.